In this lecture we will discuss the pressure drop calculations and all the considerations regarding pressure of the sample. It's important to consider the operating pressure at the sample tap and how much pressure can be used to supply driving power for the sample line. For example, even with a high sample point pressure, there may be some minimum pressure, above which the sample must be maintained at the analyzer in order to avoid problems such as bubble formation or premature flashing of the sample. Pressure at the process point and return point is very important since this consideration determines the pressure drop that is available to drive the sample to the analyzer. Ultimately, this consideration determines if a continuous return line is feasible or if the sample must be returned to an approved disposal system. To calculate the pressure drop we have two cases, depending on the Reynolds number. The first case where the Reynolds number is above 2100, in this case we use Darcy equation. Darcy equation states that the head loss equals the multiplication of friction factor, the flow velocity squared, and sample line length divided by twice the gravity multiplied by the pipe internal diameter. The head loss that results from this equation is in meters, so to convert it to kilogram per meter square, we multiply the head loss by the density. The second case is for the laminar flow, where the Reynolds number is below 2100. In this case, we use the Poiseuille law. The Poiseuille law states that the pressure drop is equal to the multiplication of 64, the flow velocity squared, the density, the sample line length and divided by twice the gravity multiplied by the pipe internal diameter and finally the Reynolds number. The friction factor in the first equation, the Darcy equation, is a function of the material of the sample line and its size. This table shows the friction factor of common sizes of stainless steel sample lines. Also, it is important to know that sample conditioning elements contribute to pressure drop and lag time and must be considered in calculating the overall sample line pressure drop. A common way to do this is to consider each element as contributing a pressure drop equal to some equivalent length of tube and adding all these equivalent lengths to the above calculated straight run length from the sample tap to the analyzer. Even pipe and tubing elbows and bends contribute to the sample line pressure drop. This table provides the equivalent feet of straight run tubing for different tube sizes and different bend angles, elbows and fittings. Let us take two examples, one on gas phase sample and the other on a liquid phase sample. In the first example, the given data is as shown in the table, mainly the process data, the rotometer setting, also you should have the lag time calculation data we discussed before. Note that the flow velocity in meters per second can be calculated from the total probe and sample line length in meters, divided by the calculated lag time in seconds. The first step is to determine the Reynolds number to determine the type of flow and the appropriate equation to use. As we discussed in the previous lecture, the Reynolds number is calculated by multiplying the flow velocity in meters per second by the density in kilogram per meter cube and the tube diameter in meters, all divided by the absolute viscosity in kilogram per meter second. Notice here the viscosity is expressed with CP units or centipoise as we discussed before, and to convert it to kilogram per meter second we divide by 1000. After we compensate in the equation, we get that the Reynolds number is equal to 12,792, which is greater than 2100. So the flow in this case is turbulent and we will use Darcy equation to calculate the head loss. Now we will use the Darcy equation. Note here we have used the friction factor from the previously discussed table for a 1/4 inch tube that is equal to 0.028, and we have added 10% safety factor to the line length. After compensation in the equation, the head loss is 226.6 meters. To convert it to kilogram per meter square, we multiply the head loss by the density. So the total pressure drop in the line is equal to 0.243 bars, which in this case very small and will not cause any problem, but let us check another example where the sample is liquid. In this example, the phase of the sample is liquid. The supply pressure is 22 bar and the operating temperature is 81 degrees Celsius. We can notice from this table that because the sample is liquid, the viscosity is higher than the gas samples and it is equal to 0.09 centipoise, while in the gas samples it is equal to only 0.01 centipoise. Also, the density is much higher than the gas samples, 537.4 kilogram per meter cube. We also note that the fast loop and sample flow is much lower than of the gas samples. When we calculate the Reynolds number using the same equation as the previous example, we find that the Reynolds number is 74,992, which is higher than 2,100, so the flow is turbulent and we will use Darcy equation to calculate the head loss. When compensating in Darcy equation, we will account for the complete line length that is equal to the probe length, plus the supply line length, which is 85 meters, and the return line length also 85 meters. After compensation we get that the head loss is equal to 31.16 meters, and by multiplying this head loss with the sample density we get that the pressure drop is equal to 1.642 bars. This pressure drop may be accepted or may cause a significant problem with the liquid sample. The pressure drop may cause the liquid sample to bubble and become a mixed phase, liquid with bubbles. This will cause a significant fluctuation in the measurement and is not recommended. We will understand later on, when we talk about sample vaporization, what are the safe limits for the pressure to avoid this problem, so that we can judge if this pressure drop is accepted or not.